Good afternoon, everyone. Welcome to MLDA workshops in the series of Foundational Machine Learning. So this is part 4 of our workshops, and here my name is Daniel Kurniadi, and I am one of the MLDA instructor, and here I'll be bringing to you materials for part 4. And in this part, we are going to go through a dataset called the bank loan datasets, and we'll perform data analytics, exploratory data analytics, and also modelings with several well-known statistical model. So let's jump straight into it. Right, so in front of me here in my laptop, in my screen, is my Jupyter notebook that I have provided for you. So maybe you can take a look after the workshop and review it again. Might be useful if you need some reference. So maybe let me tell you first about the data as well. So here, the data is actually downloaded from Kaggle open datasets. So you can actually download this data from Kaggle bank loan classification. So just Google it, or I will link you in the description below. Now, going back again, I have downloaded the data side by side with my notebooks. So you can, if you wanna perform the same thing that I done in my notebook, you can configure it in the same way like what I see here. Alright, so let's jump into it. We will first initialize our package first. So let me restart all the outputs. Right, so let's first install and import the necessary libraries that we need for doing this workshop. So we'll have some modules for basic operation and data frame operation like NumPy and Pandas. We'll also have scikit-learn as our base framework for machine learning, and it's actually a good framework for a lot of beginners like me and you, for example. And then we also have data visualization libraries that allows us to do beautiful, pretty, and cool plotting that you will see in a moment. Right, so the first chapter or the first section is we will understand a little bit about our data. In particular, first let us brief a little bit about the background or the task for this dataset. So this dataset is a universal bank data containing information about bank clients and users from, of course, the bank, that they have loans, personal loans, they have security loans, and some information about income, experience, age, and so on and so forth. Now, we'll use this data to actually predict whether, given a user data, is this user going to loan personally, or is he not going to loan personally? So that's kind of like classification problem. In more specific, it's binary classification. So let's load our data, right? So to give you a better understanding, right? So the first, let's load our data set. So it's loaded. We have 5,000 rows and 14 features or 14 columns. Now, when we do data.head, what it does is that actually it retrieves a short snippet of the data, which is the first 5 columns, as you see here. This is exactly what you see in the column, right? It has age, experience, income, zip code, family. This is family members. You can read the description here above. That's in USD, by the way. Education. This is level of education. So there is undergrad, graduate, advanced professional. There is mortgage, which is the value of house mortgage. So it kind of like gives you a hint how rich is the person is. Personal loan, this is the target that we are going to predict. Securities account. So securities here, by the way, is not security like cyber security or security like home security, but it's rather like securities in the sense of banking, business equity. So this is rather not the type of securities. Okay, so let's move forward. There is we'll try to have a descriptive, very low-level description of statistical view. We'll take a look at what's the data type, right? So all of them are probably mostly integers. That is either a label encoded or actually a real integers, like how many number of family members, right? So, and you realize that perhaps for this data analytics for prediction or classification, you don't really need so much to know about the zip code, right? Well, it doesn't give any meaning unless you know and want to do some matchmaking with the zip code in their country, but well, I don't think we need, so let's drop that. And finally, before we move on to our data visualization, let's see if our data is clean. Do we have missing value in our data? So it turns out that this data has been cleaned for us beforehand by the author of this dataset. So that's nice, but of course, real-world dataset would not be this clean or this easy, right? Most of the time, you will be do data cleaning, and if you need that, I will link the description here to learn more about how do you handle missing values. Right. By the way, I'll just move on because this is the data that we have is already clean. So let's move on into the second section of this workshop, which is data visualization. Well, data visualization allows you to understand your data better rather than just looking at numbers, right? Previously, we have data.describe, which is a statistical overview here. But, well, I just do quick glance, but it doesn't give me much information for a human like me, right? So data visualization is indeed powerful, and it kind of gives you a hint on how is the data distributed and what kind of model will suit for your data. And furthermore, it kind of like give you a lot of high level understanding that you can get regarding on how would you do feature engineering in the next step. So that's really powerful. So let's take a look at this bubble plot. So wait for a moment. Right, so this is our bubble plot. As you can see in my screen, that's pretty cool, huh? So this bubble plot or this visualization is actually kind of like give you understanding about how experience and income is related, and also it has relationship with mortgage and personal loan. So how do we eventually visualize these four relationship in one plotting, right? This is amazing. So as you can see earlier, the yellow bubble is the data or the client that has personal loan, and the blue bubble is the one that doesn't have personal loan. So this is our target, and how big is the bubble is represent the size of the mortgage, and of course the x and y axis will be the experience and the income. So this is amazing. It kind of like give you intuition that a person in, for example, in very early of their experience or their age actually has less personal loan, right? So there's not so much people that does personal loans, but as you go towards, for example, let me pick a value. Let's try it here. When you get older and older and you have more experience, perhaps the bank will allow you to have more personal loans or allow you to give personal loans because you're more experienced and you're well trusted. That's kind of like the intuition. Well, you can experiment and explore on your own. So this is the sliding button, sliding bar, that you can play with. Moving forward, you can also understand a little bit about relationship between one feature to another from something called correlation heat map. So Pearson correlation coefficient is defined as the covariance of two variables, for example x and y, divided by the product of their standard deviation. So this is kind of like hint you how correlated is for one feature to another, and this means linearly correlated, right? So for value like -1, that means the two feature actually strongly correlated, but in a negative way. So when y goes up, x goes down, and vice versa. So this is some what we call negatively correlated. So it's a straight linear line going bottom. And correlation of one, positive one, means that the two feature x and y is positively correlated. So when x goes up, so does y. And when the correlation is close or near zero, right? Well, that's not there's not so much correlation from this feature. And perhaps if you go back to your statistic, well, remind me again, but this could also hint you that maybe these two variables are independent, in fact, right? So let's take a look at the heat map. Right, so that's a nice heat map plot. So as you can see that age and experience are at the very top left here is strongly positively correlated. So as age goes, as you have more age, like, well, you have more experience. This kind of makes sense. And that also means that, well, when I want to do data analytics, I don't need both features. So that means if I just use one of them, well, I can interpret the error because they are positively correlated. So yeah, that's for correlation, and there's so much thing that you can actually get from correlation heatmap. Regarding on which data actually strongly correlated, and maybe you don't need them, or maybe there's some data that is less correlated, and that's kind of interesting, right? You might also want to see the correlation between the feature and the target, which in this case the personal loan. For example, personal loan and income is well, quite correlated, like it has 0.5 in Pearson correlation. So that's kind of like a feature you want to predict the personal loan, right? And then there's age distribution. Maybe you wanna try take a look at the distribution of your data. For example, we choose age, and it turns out that when you plot this age distribution, well, interestingly, it's uniformly distributed, right? So it's well distributed and well balanced. We might also want to take a look at several visualization for our binary feature. So our binary feature are this one, personal loan, securities, account, CD account, and online and credit card. So this is the feature that has yes or no, and that's all the feature, like 0 and 1, which indicates whether, yeah, again, yes or no. So for that, we can actually visualize this data by using one of them is using donut charts. So let me show you what I mean. Now, in front of my screen are this chart representing the distribution of each feature, and well, you can already see there is some imbalance in the data. And in addition to that, you might want to infer, like for example, the distribution of personal loan, right? So this is our targets, and it turns out that, well, there is, in general, in overview, not so much of the bank client actually take personal loan. So only like 6.9% take the personal loan. And if you are going to use this data set for predicting whether a client will take a personal loan or not, well, just to remind you, there might be you might suffer from imbalance of data set that you might need to handle. All right, so moving forward with our plottings, you can also plot the relationship between one feature to the target. For example, with this family members towards personal loan, the more family members you have turns out to have quite positive negative correlation, because turns out the more family members you have, the less you will the more, okay, that's positively correlated, that the more you will likely to have a personal loan, right? And education versus personal loan, you can also do the same thing, and turns out that well, people with higher education tend to have loan, perhaps because they are more well trusted, and hence given the loan by the bank. There is, of course, income versus personal loan as well, which also indicate that the higher income you have, well, the more stable is your finance as an economy, and the more likely you are given uh, the loan from the bank. Right, so that's kind of our data visualization. So finally, mortgage versus personal loan. Well, there's not so much relationship here, actually, if you can infer from this visualization. And if you go back again to the heat map, it turns out that you can verify yourself. There's not so much correlation between personal loan towards mortgage. Now, with that, you kind of already know which feature are kind of like useful, kind of like have strong correlation to each other. which is not, and which features are discriminant enough for classification, personal for doing classification. Right. So for section 3, we are going to prepare our datasets, a little bit of data messaging, right? So the first feature engineering that we are going to do is to convert categorical columns to dummies. So what I mean with dummies is, if you know, it's called one-hot encoding. So let me just search it quick. One-hot encoding, right? So one-hot encoding is kind of like represent your categorical feature 1, 2, 3 into a factor of 1, 0, 0, 0, like 0 and 1s. Now, our feature or our data has several categorical columns. For example, education columns. Well, it represents a data for each user where 1 is represents undergrad, value 2 in education represent graduate student, and number 3 represent, I think, would be PhD student. Let's take a look. Yeah, advanced or professional, so I guess it's a PhD. And the same thing goes for personal loans, securities account, CD account, online, and credit cards. So those are categorical feature that we can actually convert to one-hot encoding or dummies. The reason so is because, well, for one, your model understand better factor rather than encoding and this categorical encoding. And in addition to that, categorical encodings like 1, 2, 3, 4, well, it doesn't have any sequential meaning. Like for example, 1 doesn't mean it's better than 2 in this case, because being undergrad and being graduate student doesn't have this well, a numerical ranking, right? I guess, arguably, so it's better to use categorical encoding. Now, we can also to prepare for our training and validation evaluation of our model, we will split our data into training and testing set. So our training dataset would consist 80% of the data, and our testing will consist 20% of our data. So the reason so is we would like to separate or kind of like take some portion of our data so that we can use it to test our model later. So why don't we test on the same, well, training data set, right? Well, it's because we want to validate or we want to evaluate our model for the data that these models has never seen, and evaluate that the performance of our model on that data, the data that the models never seen. And we are more interested in evaluating in this testing data set in the testing accuracies, because it represents how well your model generalizes to data in real world. Right, so we'll split our data. So it becomes 4,000 and 1,000. We'll also do a final preprocessing, which we will standard scale or normalize the value of our data into, well, we'll normalize that to 0 mean, and we'll string the standard deviation so that it's standardized, and it's kind of like allow our model to you know make it easier to backpropagate because it has a standardized value. Imagine if you have different, for example, different scale for different feature, like for example money in thousands of dollars, but at the same time age only ranging in 10 or like 0 to 100, kind of like make it difficult for your model to backpropagate and to perform gradient descent. I'll link a better description for why do we need to normalize our data in the description below. Moving forward, so I'll standard scale our data. We'll move forward to section 4, where we'll perform classification modeling. So this is our core in this workshop series, classification modeling. So this is kind of like a follow-up from the previous workshop, where I'm putting what you have known about classification to real-world data. in a kind of like end-to-end manner of data science workflow. So the first model that we are going to experiment with is logistic regression. So logistic regression, despite its name, is actually a linear classification as rather than regression. Well, logistic regression is, if I may put it simply, is actually a linear classification, but at the end of it, you pipe the output to a sigmoid activation function. Let's dive into the code, right? So we'll instantiate a model, a logistic regression model, and we'll perform a model fitting with our training set as such. So we can so afterwards we have fit our model. So our model has learned, and it's time to evaluate our model, how well our model actually performed. So we'll perform evaluation on the training data that the model already sees, and we'll also perform evaluation on testing data that the model has not seen before. And it turns out that the accuracy is quite good. We have a 0.95 and 0.96 for the training and testing accuracy. We also convince further ourselves by performing a better evaluation methods called cross-validation. So cross-validation works by splitting your data into several several faults. That's what they call it, and you perform each validation for each faults, and then average the performance result across all the faults. And this is better because maybe in case you're actually performing a testing on a data that might be easier than another portion of your dataset, for example. Right, so we perform cross-validation for logistic regression, and then we display the evaluation results. Right, so as you can see in our data, first, our cross-validation score accuracy for testing turns out to be really good. It's 0.96. I would like you to focus on the confusion matrix because, it turns out that you can already see here in our confusion matrix that our negative class or class 0, which denotes the user or data points where it's not taking any personal loan. Well, it turns out that there's an imbalance here. So how does that affect us? I would like you to think through while I'm going through this part. So let's also calculate the precision, recall, and F1 score, right? And afterwards, we can do the same thing with another models or classifier. In this case, we are going to use Gaussian naive-based classifier, which actually uses naive Bayesian concepts to actually perform prediction. So this is kind of like probabilistic prediction, and it assumes that your feature is Gaussian distributed, and your feature are independent towards each other. Right. So the same way, I'll run this cell. I'll also, after I fit my model, I will predict I'll perform a prediction to eventually evaluate my model on training and testing data. Right. So it seems that our naive Bayesian is achieve less accuracy, or should we say less performance, and then we'll also plot the confusion matrix and calculate the F1 score. Now, that is more or less how you would perform evaluation on your models. And that's really quick if you have only like 5,000 datasets. Now, let's see actually I want you to take a look at our confusion score again, right? So because it turns out that even though your model has a good accuracy, like in this case 0.9%, but it turns out that your model performs badly given the ground truth is actually a 1. So for personal loan data, your model is not actually that good at predicting. And this is kind of like, well, for certain application, it's important. Because in this case, perhaps if the data or the ground truth is 0, you don't really bother with wrong classification. But maybe if your ground truth should have been 1, you kind of like bother to have this data point correct. For example, in fraud prediction or fraud outlier detection, well, outlier are very scarce, like what we see here, and it creates an imbalance data set. So when you do or you perform an accuracy metric evaluation, of course you would see a very high score. But what happens is your model actually or tend to just classify every data points as, for example, in this case, 0. So it kind of like when there's an outlier, your model will fail to predict that. And that's terrible because essentially you build an outlier detection to catch that outlier or frauds, which has class 1 usually. So that's the insight that we have so far. And again, if you don't believe me, there's an imbalance. I'll plot this bar chart so that you can see that the personal loan data with personal loan equal to 1 is actually very low. So we have an imbalanced data set problem, right? So how do we mitigate this imbalanced data set problem? Well, as you can see, that accuracy, top 1 accuracy, is kind of like a trap metric that actually doesn't give you the real insight of how your model perform, especially with unbalanced classes. Especially if your classifier always predict the most common class, well, that's kind of like your model, yes, sure, it will achieve a good accuracy, but it will not predict well given the minor class category. So first thing that I would suggest to you is use another evaluation metric. So there's many evaluation metric. We have used confusion metrics, precision, recall, and F1 previously, right? So this is something that I already give to you, and I would like you to search yourself, have your own individual independent learning on what are these evaluation metric means. What is F1 score? What is recall, right? And perhaps if you want to dive further, then how does it relate to AUC ROC score? Right. The final one, the next part that I want to advise you on how you combat imbalance dataset is by imposing a weighted loss in your model. So recall that in loss function, let me scroll up here, right? So you have this loss function, which is in this case is our logistic regression loss, and you can eventually add a weighted loss. So for data that is a minority class, you might want to impose more weights because you want to ensure you punish more if your model is getting wrong on this particular data type. So for you want to make sure your model really learn that for outlier class or for minority class, your model have to get it perfect as or even better than the majority class, because the minority class because of its very scarce and very imbalanced amount, your model have to get it right, and it's harder for your model actually. So this is why you will use a weighted loss for in your model. So you can do that easily in scikit-learn by giving this option class weight equals to imbalance. So if you search that scikit-learn logistic regression with, I just want to give you this documentation that if you use balance mode, it will automatically adjust in your class loss inversely to your class frequency. So that's how it works, and that's kind of nice. So you can see that eventually your model is getting a little bit better, right, than the previous model. So your recall score, look at this, it's become, well, much better, but is it good enough? So we'll take a look at the next method, which is called resampling. So there is two type of resampling. One is undersampling, and another one is oversampling. We use these sampling techniques to deal with highly unbalanced dataset, and it consists of, well, for undersampling, it kind of like removing samples from the majority class at random, and for oversampling, it's kind of like adding more sample from the minority class. And of course, this means there might be a duplicate dataset, but at least this is kind of like a common way to go, right? So let's see how we can do that. First, we'll count the number of class and divide the class or data by class, and then afterwards, for undersampling, we can eventually perform sampling by using this function class your data. This is a pandas data frame object dot sample, and you sample as much as class 1, right? So you sample class 1, so that's undersampling, and this is what you get. So your class 1, right, or your, that is kind of like your imbalance dataset or your minority is actually, well, more or less has the same count as your majority dataset. Another approach is to do oversampling. This is where you do the otherwise. You sample from, instead of you are sampling from the majority dataset, you are sampling from the what do you call it? Minority dataset, which is in this case is class 1, right? And then let's see our dataset distribution looking good. And finally, we can go further. Well, I'll choose this method to go forward with our modeling, right? So this is just an example for you. Then afterwards, we can perform pretest split again for our resampled dataset that has been balanced. And then let's redo. Let's go back into modeling again, but this time we're going to perform hyperparameter tuning. So this brings us to the next section, section 6, about grid search hyperparameter tuning. So we can, so I define a function here, which is basically what we have encapsulate what we have done in the previous part in our modeling, which is first initializing class, perform evaluation, and display the evaluation results. All right. So that's this function is all about, and I'll also list out the hyperparameters that to be grid search upon, right? So rather than having just one configuration, I might want to experiment with several configuration and hyperparameters for a particular model. So how do I do that, right? Well, you can do copy paste again, but that's not so neat, and there's a much cleaner way to do that, which has been provided by this machine learning framework. So sklearn has something called a grid search, which eventually handle this hyperparameter tuning by, well, brute force. This is kind of like trial and error. But of course, if you are using, let's say, Google AutoML, there is an algorithm like that does that in a smarter way, so that you don't have to brute forcefully search all the parameter space. Right, let's try for key neighbor classifier. So it turns out that after grid search, the best model is the model with that uses Manhattan distance metric and uses neighbors equals to 5. You are free to actually experiment with by adding more parameters. For example, for key nearest classifier, you can have 5 neighbors to depend on. You can have 10, for example, 15, 20, and so on and so forth. And you can have this different distance metric. I'll refer to you to the documentation itself, sklearn KNN, to actually learn what is k nearest neighbor classifier and what's its hyperparameters. Finally, we have this evaluation results. And if you look again, our confusion matrix and F1 score will be it's much better now with a balanced dataset. Well, let's move forward. We also have support vector machine model we can try on. Let's run our grid search and cross validation. Wait for a while because support vector machine actually quite computationally leading, so you kind of need to, you know, be more careful when you wait for a moment. Okay, yeah, so this is our support vector machine. It actually achieved very good performance actually. And then moving forward, we have random forest. Random forest, if we perform the same thing, wait for a while. Right, so that's our result. And pretty much the same thing for adder boost classifier and gradient boosting classifier. So in the end, that's kind of like one example of how would you do or how would you perform data analytics given the datasets. For the theory parts or the concept itself about what's the key number classifier, what's support vector machine, what does it do underneath the hood. Well, I'll refer you back to the previous workshop that we have that I think my colleague has delivered, and I'll also leave it to you for exploration. There's a lot of documentations, handouts, like lecture notes from Stanford, from MIT that you can actually learn to enrich your understanding in modeling. So yeah, that's pretty much our workshops. Look at our notebooks. It's quite colorful, isn't it? So I hope that as colorful as this notebook is your understanding in machine learning. So thank you so much for watching this video. I'll see you in the next tutorial. Thank you.